Okay, thank you. Next speaker is by Twain Byrnes from CMU, automatically enforcing Rust trait properties.
All right, hi, I'm Twain Byrnes. I use they, them pronouns, and I'm presenting joint work with Yoshiki Takashima and Limin at Carnegie Mellon University on automatically enforcing Rust trait properties. So the first question you might have is, what are Rust traits? These help define shared behavior abstractly. So if you've ever programmed in Java, they're very similar to interfaces. And Rust traits often have invariants. These are things that aren't checked by the Rust type checker, but still need to be true in order for the Rust trait to be valid. So for example, partial equality needs to be both transitive and symmetric. Just things that you would expect of a partial equality relation. These traits are often already implemented for the standard library types, but for user-defined types, it's often nice to be able to implement these yourself. So for example, if I had a custom type called object ID that has, say, an ID field that's just a length 12 U8 array, that's this right here, then I might want to implement the from trait. And so the from trait just converts from one type into another, and its invariant is that it's not allowed to crash. So in this case, we just take in our U8 array of size 12, and we just put it into that ID field. This won't crash. This is a valid implementation of from. So the problem that we run into is in formally verifying these trait properties. So we find that trait properties are often unchecked in a lot of real-world code, and when they are checked, it's usually through unit tests or fuzzing. And so we also wanted to increase access to formal verification. And so to go about this, we decided to encode some invariants as Rust assertions, and then use a Rust verification tool to verify these assertions. And just to make it all easier to use, we created a UI integrated with VS Code. So since we had to use just some Rust verification tool, we decided to use Connie. Connie is a bounded model checker for Rust. It verifies assertions for all inputs of a certain type, and it's best for bounded types, like U64s and I32s. So I thought I'd give just a brief example of a Connie test. So if we have some function called return even, takes in a U64, outputs a U64, does something, doesn't really matter, but we want it to always return an even number. We can write a Connie test for it that looks kind of like this, where we set some variable num to be of type U64 and just take on some arbitrary value. And then we assert that when we pass that number into return even, mod 2, it's going to be equivalent to 0. So just that return even will always return an even value. So our tool is able to support the following traits. So from and into, which just convert between types. It supports partial and total equality, partial and total orders, and asmut and asref, which convert between mutable instances and references. So here's a quick demo. It's just going to add a test for, on line 118, we have partial equality implementation for lim, which is just a custom data type in this library we were looking at. So if you just click the add trait test button, and then when you save the document, you get a little play button that lets you run that Connie test. So as you can see, we have these first 3 lines here just set up our variables. The next line does the symmetry check, then the transitivity check, and then just another additional check to make sure there's consistency between not equal and not equal, and the other way around. And so then you get this little check mark showing that the test does actually hold. And explaining that took a lot longer than it did for the test to run, so we can see there's not a lot of overhead with this, which is really nice. So with this tool, we ran 42 harnesses on 6 popular Rust traits. We found that the majority of the verification time was under 10 seconds per trait instance, so again, very low overhead. And we were able to find 3 issues in Prost, which is a protocol buffer library with nearly 40 million downloads. So one of the bugs that we found was a potential multiplication overflow in converting between custom types storing the date. And so there was this year to seconds function that on line 3 here, obviously I skipped a bunch of stuff, but we're doing some multiplication by 31 million something. And Connie returns that, I'm not even going to try to say that number, but if you try to convert from that year into a different year, you might have a multiplication overflow. And obviously this is not a real year that we would see when we were trying to use this function, but it is potentially exploitable. So for future work for this, we would like to create transitivity for partial equality and partial order across more than 2 types. Within a specific instantiation of either of these, you can only have, you can only declare it between 2 types. And this tool currently only looks at 1 instantiation at a time, but if you declare it for 3 or more types across multiple instantiations, it needs to be transitive across all of them. And also, our tool is limited by the capabilities of Connie. So Connie currently has problems with performance on large crates. With polymorphic types, it needs a specific instance, and it has issues with concurrency as well. So all in all, our tool helps make formal verification for trait invariance available to all Rust programmers with no formal verification experience required. You saw, just click a button, adds the test, click another button to run that. And it's enabled by our fully automated harness generation tool. And if you want the GitHub, that's just at the QR code there. Cool.
Thank you. Questions? Yes, on the back, 2 questions.
Does Connie handle unsafe Rust? And if not, do you know, is it common for these trait implementations to use unsafe Rust, or is that more or less a non-issue?
Yeah, so I'm pretty sure that Connie is able to work on unsafe Rust. Yeah, there are some traits that can be used unsafely. The crates that we were looking at, it was all within safe Rust, but we were looking to expand to that.
Can you talk about the user experience of diagnostics? So when there's a failure, what information is presented to the programmer, and does it seem to be sufficient in your experience of that, like, people can take that information and solve the problem, or are there things to be solved in helping people understand this this kind of feedback loop?
Yeah, definitely. So I mean, if you ask for it, Connie can give you an example of a bad number, which doesn't necessarily tell you exactly how to fix the problem. It does say specifically, you have a multiplication overflow on line this, you know, with whatever value, like this one. And so, I mean, I think that's nice.
Does it also localize in the proof, I assume? Like, you have this big proof statement, and it says, like, oh, like, it's this specific assertion.
Yeah.
These sets of inputs, right? Okay.
Yeah.
Got it. Thanks.
Another question, final one?
If in a trait for equality, for example, you use the equalities of underlying types, does the model checker like unfold all of that, or is it assuming the equalities used of included types are correct?
Yeah, so Connie will verify that even a standard implementation, like an implementation already within the Rust library, Connie can verify that that actually does follow the invariance. So if you asked it to verify, so if we take this test here, and if we just put partially Q, and instead of A of type lim be Connie any, ABC of type lim, if we just set that to like I64, then it'll verify that it does follow these invariants.
But is it rechecking essentially stuff we should have already checked somewhere else? Like, is it?
I mean, it is potentially rechecking stuff. I don't know that I would say that it should have been already checked.
Thanks.
Yeah.
Okay, thank you again.